Let's do a video on a PWM DAC with a first order low pass filter. So here's the circuit you need to build. Here's the proto board. I have to use a camera to see the 102, which means that's a 1 nanofarad or 0.001 microfarad. So build that and connect it to your SCopy and click on your network analyzer. Sweep 1 kilohertz up to 200 samples. Any more than that, and take a little bit long to run. And if you go for frequencies lower than you have to, it can take a really long time to sample those low frequencies. So right here is our 3 dB point, which is pretty close. Sorry. About 3 dB. Frequency is about 7.37 kilohertz. So that's our cutoff frequency. But we can see that the phase never goes actually to 90. It's 81, and then we see this resonant peak due to the parasitics, which we can see the effects of that if we do square waves. So go to a signal generator, and I use as large a signal as I can so that the digitizers can digitize as much as they can. So 10 volt peak to peak, 50% duty cycle. We'll start off at 1 kilohertz. And just to show you how it works, set the offset to 5. Run oscilloscope. And then run the oscilloscope. And you can see that we're getting our step response, right? And that rise time should be our 5 tau. All right. So now let's start to bump up the frequency. Let's try 10 kilohertz. You can see we're starting to get that triangle shape, and the peak to peak is 4 here, and the peak to peak is 5 and change. So we can only get 1 inside, right? So that's like a 1-bit DAC. Oops. Let's jump up to 100. Notice the mean is going to 2.4, which is 50% duty cycle, should do that. All right, and the peak to peak is 800 millivolts, right? So if I divided that into the peak to peak of what we're measuring over here, well, I found some of the measurements aren't to be trusted on that. If we say it's 10, it's 10. Sometimes it doesn't quite measure correctly. But this is that ripple that we're measuring. And you can see that that ripple might fit 1, 2, 3, 4, 5, maybe 5 levels. So if we increase the frequency, the filter will filter it more. Try 500. And you can see that it's pretty flat, right? Now, 50% duty cycle gives you the worst ripple, right? But we can set this to 10% duty cycle. And see, now it's at 10%. We can set it to it's not 100, 90. You can see that it's raised up there. Now that's great for seeing it, but to measure the ripple, it's actually better. What I found is to take away the DC offset, because we don't really care about the average. We're trying to measure the ripple. And this makes it a lot easier to zoom in on the functions. Worst case ripple will happen at 50%. We can go back to 10 kilohertz. Right. And you can see that's our ripple, right? But when we zoom in or increase the frequency to 100, right, you can see it's reduced, and then you can start to zoom in. I'm going to turn off channel 1, and you can see these oscillations, right? And so our ripple isn't as small as it should be because of these oscillations. This is due to the fact that we got this resonance circuit out here, right, due to parasitic capacitances and inductances. And this can be quite severe, so you'd think that the highest, so even let's take it out to megahertz. Right, that's right when that's starting to happen. We can zoom in, but see the ripple, the bouncing, is greater than the sine wave. And so it actually limits how good it can be. Now the solution would be to use capacitors and inductors, resistors and capacitors that were specifically designed to not have parasitic devices, and then we get a lot cleaner response. If we take the signal generator, let's put it right on the cutoff frequency and look at the spectrum analyzer. By the way, everything is set to rectangular. You can see this is the input, which follows what you would expect, and then the higher frequencies are in fact attenuated, which is what's happening. Not quite sure why I'm getting the noise. I think it doesn't. Yeah. I'm probably just stepping over the noise. But you can see this follows the pattern of a 50% duty cycle. This is 1/2, and this is the attenuated part, right? That's 3 dB, which is practically, right, 0.7 of whatever. And then it gets attenuated more and more as that filter comes into play. So do all that for your filter, right? But your cutoff frequency will probably be a little bit different. Your residence might be a little bit different, but you should be getting a low pass filter with some non-idealities.